Hello, everyone. In this video, I will be demonstrating how to conduct measurement invariance among dyads using the lavaan software within R. So the first thing that we will do is that we will set our working directory. So I have actually set it for the session, but I will show you how to do that if you are unfamiliar with how to use R. And so we'll go into choose directory, and this is the folder where I have my data file. And so I will go in, and it's normal not to see anything here, and I will just click open. All right, so that tells lavaan where I am pulling my data from for this session. And so you will see down here, you can, it says set WD, and that means it's set a working directory, and then it gives me a path name. And so that is telling lavaan where we want our session to be focused within our computer system. So if you do not already have packages installed, installing packages in lavaan is quite easy. So down here in your console, I'll make it bigger. So you can go to install .packages, and then you type in a parentheses, and then you'll type in quotes, and you will type in the package name that you are wanting to download and wanting to install. So I already have lavaan installed, but yeah, so that this is an error message you're getting, but you would just hit enter, and then it'll download everything for you, and it will install everything for you. And then the second uh, package that we will be using is called Haven. And so what Haven does is it allows you to bring in SPSS files into R with a lot of ease. So those are the packages that we'll be using here today when testing measurement invariance with dyad members. So we will first start off by looking at the syntax. So here to load the packages, I just typed library and then type the package name. And so I did Haven and lavaan. And then the first thing I'm doing is I'm creating a data object. So they are big on objects. And so a lot of the times, or actually every time that you use R, you're going to have to create an object that has your data stored within it. And we will also see that happen when we want to get our summary statistics for our structural equation models. What you'll see is that we can actually run our SEM models, but if we don't create specific objects with those summary statistics, we're not going to be able to see our parameter estimates, our fit statistics, or really anything else. So that will be something that we are doing quite frequently. So once you have specified, loaded your packages, set your working directory, and created your data object, then we can begin to move into creating our confirmatory factor analysis and our model. So briefly, before diving in there, we can take a look at the data file. And so you will notice that this is in wide format. And so here, this first column is the dyad number. And so we've just randomly created some numbers for the dyads. And then you will see any variable that has an underscore M means it's reported by the male partner. And all of the dyads in this data set are cisgender and heterosexual. All right, so you can scroll left and you see some item level data that we'll be working with. And then you see some composites. And then you can keep scrolling, and then you hit these arrows up here to scroll further, and you will begin to see data without that underscore M, again, which indicates that it will be the female partner reporting on the item or the scale. All right. And so now we'll create our first kind of model. And so again, this is kind of up to you in terms of what you want that to look like. I do cfa.config. That's what I wanted to call my model. And then I use these arrow signs, and then you'll see there's one quotation mark up here, and there's another quotation mark down here. And everything in between is everything that's going into this cfa.config model, right? So the first thing that we're going to be doing is creating the latent variables of relationship mindfulness. So the relationship mindfulness measure was answered by both male and female partners. And it's 5 items, and they're rated on a 1 to 7 Likert scale. And so we are going to create a factor model to estimate the factor loadings, the intercepts, the variances, covariances, and all the things like that go into factor analysis. And then what we're going to do is we're going to compare those latent means across those dyad members as our kind of our final step. So our first step is to create the latent factor for the males. And so in lavaan, you will specify your latent variable by creating a name for it. I just chose relationship mindfulness measure RMM_M to indicate it's the male reports on relationship mindfulness. And so you will notice that I have the 5 items, RMM 1, 2, 3, 4, and 5, all of that reported by the males. And then you'll see I have value labels before the variables followed by an asterisk. All right, so what this does in lavaan is it creates a value label, and that will come in handy in the next step when we are testing metric and configural invariance. But to briefly foreshadow what these do is that variables with the same label, so we'll say lambda1 and lambda1, those will be constrained to equality in lavaan. So we don't want to do that just yet, but that is what we will be doing in subsequent steps. And so I just included the value labels beforehand because I know I'm going to need to add them a little bit later on. So it's just kind of getting ahead of myself a little bit. And that way, programming and entering in the syntax for the metric and the scalar models is going to be a whole lot easier. And so you will notice that none of these labels are the same because we're not at that step yet. So it'll just be lambda1 through lambda10 is the notation I gave for it. And lambda indicates a factor loading if you're using Lisrael notation. We're going to do a very similar process with the item intercepts. And so I am doing, again, pretty much the exact same thing where I have relationship mindfulness, item 1, 2, 3, 4, 5, all reported by the males. In lavaan, you use a single squiggle to indicate a regression coefficient. And then I have my value label and *1. So that is lavaan's notation for estimating the intercept. It might appear a little funky, and it took me a little while to kind of get used to it. But if you've ever seen a path diagram, and you've seen a perhaps more complex path diagram, is oftentimes there's going to be a triangle with a 1 in it, and that indicates a mean structure. And so I don't quote me on that. I believe that is the rationale for having this 1 there in relation to the intercept. So that is how I understand it. And if there's alternative explanations that Yves Roussel did when creating lavaan, then we have a happy coincidence. But you will see those triangles in mean models, in latent variable mean models, quite a bit in SEM. But if you're just estimating covariances, they tend to be a little rare. For example, you'll see it a lot in growth curve models, is probably where I see it the most commonly. And so we do that, label the item intercepts for both male and female. And again, I have it tau 1 through tau 5 for male and tau 6 through tau 10 for female. And I chose tau because in Lizarel notation, generally tau is going to be those item intercepts. Right? I've also heard new being used, but I see that far less often. Tau is generally the Greek letter assigned to item intercepts. And then finally, we are going to estimate our covariances. And so we are going to have 6 covariances. I will start at the bottom with perhaps the most common one and that is we're going to allow the latent variables of relationship mindfulness for the male and female partners to correlate, right? This is focused on dyadic data. And so obviously we're going to be dealing with issues of non-independence. And so what we're going to be doing to account for that non-independence is exactly what we're doing in like an actor-partner interdependence model. And we're just going to throw covariances on there. All right. So we do that at the factor level. Okay. And we're also going to do that at the item level. So we are going to correlate the residuals for the male's report on item 1 with the female report on item 1, her residuals. And we're going to do the same thing for item 2 and for item 3 and for item 4 and for item 5, again, to account for that non-independence. We cannot assume that all of the non-independence is accounted for by this factor when in fact there might be something unique that the question is assessing that might occur above and beyond the what is accounted for by the factor. So I believe foreshadowing 1 or 2 of these is statistically significant and 3 of them are not. So you may not see statistical significance, and it might be that most of the interdependence and the correlated errors that we find in nested data is taken care of by this covariance between the latent factors, but that's not always the case. So we never want to make those assumptions. Otherwise, without these, we are leaving ourselves at a greater risk for biased parameter estimates. And so what that will look like is if we exclude these and there really are residual covariances that are perhaps pretty small, you will see higher factor loadings for both partners, and you will see a much stronger covariance between the latent factors. So those associations that the model is trying to account for that are getting suppressed because you're not estimating that residual covariance is going to pop up in the factor loadings and the residual covariances, because that is how that if you do path tracing rules, that is how the variables are associated within the model, right? And so now we'll go down to our next object. And so we're going to create an object that stores our fit statistics. And so I'm just calling it fit.config. And this will be, you can again name this whatever you want. I'm using the SEM feature within lavaan. I believe they also have a CFA feature, but I tend not to use some of those specific aspects of the CFA feature. And so I just use the general SEM feature, but that may be of actually great utility to those of you who do a lot of factor analysis. All right, so up right here, we have our model from up above. We want to specify our data object, which is from up here. So if you are a SAS user, then you are probably very used to this. I think people say R and M plus are very similar. I think it's actually way closer to what you do in SAS and the coding procedures in SAS. So in this object, I want to specify that we are using maximum likelihood. I'm specifying that we are using full information maximum likelihood to address missing data. I believe we have something like 99% complete data, and so it's not really an issue, but We will not always be that fortunate to have such low levels of missing data. And then we want to include the mean structure because we will eventually be testing latent means, and we want to be able to utilize that mean structure. All right, in our summary fit, we're gonna request all of these pieces of information. We do want fit measures, CFI, TLI, RMSEA, chi-square. We want standardized regression coefficients, right? And then we want to know the explained variance for our indicators. And you will also notice that I am requesting some local fit indices. So the RMSCA, the CFI, the TLI, the chi-square, those are omnibus measures of model data fit. And so their job is essentially taking a 30,000-foot look at the model and saying to what extent does it fit the empirical data. And if we have our fit statistics that are, 0.95, 0.96, 0.97, 0.98 for the CFI and TLI, our RMSCA is like 0.01, our chi-square is insignificant, then we can say we have a really great fitting model. And there's probably not a whole lot of need to poke around. There might be a little bit, but not all that much. On the other hand, if our CFI and our TLI are around 0.89, so they're below recommended thresholds outlined by Hu and Bentler, then we will need to poke around because that is telling us that the way we have specified the model is incongruent with the data and we need to make revisions. Perhaps we're thinking about it incorrectly. Perhaps we got a rogue item. There's a lot of things that could be happening here. But that's something that we need to know. The problem with these global fit indices is that they can tell us there's a problem, but they have no way of sharing where that problem is. So again, there's probably 5 or 10 different things that I can think of just off the top of my head that could lead to poor model data fit. Excuse me. And these global fit indices do just a tremendously poor job at telling us where the problems actually are. And so what we're going to do to combat that is I want to get the residuals. And so this is your expected covariance matrix. So it's the sigma theta. And you subtract sigma theta hat, which is your observed covariance matrix. And the output is the difference between what the model expected and what the parameter estimates actually are. And then you can subtract them from one another, and then you will get scores, and then we can even throw a z-score on them. And what we'll see is that scores that have a negative value are going to indicate that the model is underestimating the associations, and we'll find that the positive values results in an overestimation of the associations. And then I have modification indices here, which again are another indicator of local misfit, where the lavaan goes in and says, if you just add this parameter, then your chi-square is going to go down by 12. And these modification indices are completely detached from theory. Lavaan does not care about your theory in any way, shape, and form. And so we have to be exceptionally careful around modification indices to make sure that they make theoretical sense, and that we're not just capturing idiosyncratic nature, the idiosyncratic nature of our data. Because if we throw let's say a residual covariance between 2 of the items in, because there's some other external cause that is wanting them to correlate with one another, that might be a function of only our sample and might not be true of the population more generally. All right, so we can go ahead and we're going to run our configural model. Pop that up. All right, so I'll make this bigger. So we'll start at the very top. And so when we're using or testing, I should say, configural invariance. Generally, the test is model data fit. That's going to be the best way we can test the factor structure of our data. And so essentially with configural variance, that's what we're trying to accomplish, that factor structure. But that can be quite vague, and that can be kind of confusing and not really tell us a whole lot. So when we're considering the general factor structure of configural invariance, we're saying, are there the same number of latent variables among males and females in the sample? Are there the same number of residual covariances? We estimated 0. Does that apply to both male and female? Are there the same number of items even? Perhaps one of the items perhaps has a gendered effect, and so that is dropped. That would not support configural invariance. So there's a lot of reasons for there to be not for the factor model to be configurally non-invariant. All right. But essentially, we are doing quite a simple model, one factor with 5 items. So we don't run a high risk of having configural invariance problems. But the more and more complex your models get, the more and more likely it is that you will run into such issues. All right. So we have 305 people, and so that's how many people in the data set. So I know I didn't lose anyone to missing data. We have 29 degrees of freedom. So we are estimating 29 fewer parameters than we have the capacity to, which is good. We have a chi-square test. This is a highly powered test, and it is exceptionally sensitive to even small deviations between sigma theta and sigma theta hat, which is your expected versus in your observed covariance matrix. And any small deviations between those two matrices is going to be captured in your chi-square statistic. If you're a multi-level modeler, the log likelihoods, which we'll see down here, which are somewhat related to a chi-square, are overall indicators of model data fit, and they are what's called deviance in that multi-level model. But in the SCM, we have additional fit statistics that the multi-level model doesn't have, including the CFI and the TLI. So both of these should be above 0.95, give or take on average, but we don't want to hold every single model to that requirement, because decades of simulation research since Hu and Bentler in '99, since their seminal paper, has shown that a lot of these fit indices are they function differently based on different characteristics of the model. So, for example, the RMSEA is a per degree of freedom or per restriction estimate of misspecification, and so it takes into account sample size. But what happens is that when there are very few degrees of freedom, your RMSEA tends to either, at least in my anecdotal experience, either it tends to be 0 or it tends to be like 0.10 and above. There's not much in between when there are small degrees of freedom. And so when running models like that, I tend not to use the RMSEA. But we have 29 degrees of freedom, so the RMSEA is probably going to be functioning okay in this type of model. But that is an example of being careful and not just using Hu and Bentler as a end all be all in terms of cutoff scores, because the reality is you could have a great cutoff score of 0.90 or 0.89 even, due to characteristics of your data, such as sample size, extent of covariation, the use of latent variables, and things of that nature. All right, so our RMSEA is good, our CFI and our TLI are good, our chi-square is non-significant. So all of this points to configural invariance, so we are good to go. I'll just take a glance down here at these. At this point, I don't place a whole lot of emphasis on interpreting the factor loadings because we're going to get increasingly more restrictive. So these estimates are going to change in subsequent models. So I don't really see the need to make a big deal about interpreting them at this point. But what I am going to do is I know I'm going to be constraining factor or loading one in males to loading one in females in the next model. And I'm doing the same thing with 2, 3, 4, and 5. And so I'm just beginning to look at these unstandardized estimates. So everything in estimate is unstandardized. All right. And actually what I'll do is I'll annotate this. And so that hopefully that will make things a little clearer. So we have our unstandardized here. All right. And so again, I'm taking a look. So 1.30, 1.17. So not a whole lot of difference. There might be something there. 1.23 versus 1.22 or 23 if you round. So again, they're almost identical. 1.439, 1.503, 1.41, 1.56 or 46. So all of those give me an indicator that we're probably going to find something non-significant with metric invariance, but you never know. But it's nice to kind of get a general feel for your data, because if you don't have complete invariance and your chi-square difference test that will run is non-significant, then you'll have a good sense of what might be the problematic child, of which one of these loadings is misbehaving and which one do you need to go put in timeout. All right. And so these are unstandardized loadings. So here are your standardized loadings right here. Your standardized all, so that's you're standardizing your latent variable as well as your observed indicators. And so that these will be interpreted in the exact same way as a beta weight from your multiple regression that you are all so familiar with. And then we also have our let's put this down here, are residual covariances. And so as I had mentioned before, there's only a couple of them that are significant. So we have these two right here. This one's kind of sort of doing a little something, but isn't all that meaningful, and it's above 0.05. The only one that is really sticking out to us is this one, and this is not a residual covariance. This is the covariance between the latent factors, and the correlation is 0.631. So if we square that, then we can get an estimate of about how much variance is shared between dyad members, and this will put it around somewhere 40%, maybe just under. So and so that'll give us some indication of how much, again, variation in relationship mindfulness is shared across dyad members. And then the same thing with intercepts. Again, so here's all the male intercepts, these 5 guys right here. So again, I'm kind of just, again, very much eyeballing it, no sophisticated statistical analysis needed. I'm just beginning to anticipate any potential future problems. And here I'm looking at comparing the male and the female, and I'm not seeing a whole lot of potential problems, which is good, but we'll let the results really truly tell us whether or not these are significantly different from one another. All right. And then down here, we have our variances of our items and our latent factors. All right, so we have a variance of 0.529 and 0.457. So that means there is variation in the scores on the latent construct in males and females, and that is indicated by to be significant by these p-values right here. All right, so we can kind of push this down, and then we can move on to metric invariance. And so what I am doing in metric invariance is essentially the exact same thing as configural invariance. I am just going to be placing restrictions on the factor loadings. So that is the only change I'm going to do. And so as you will see here and see again when we test scalar invariance, invariance testing is hierarchical. So all of the restrictions that you uh, uh, placed in the previous model are carried forward into the current model. All right. And so how do I constrain those factor loadings to be equal? I just use these value labels. So you'll see I actually changed up the label here. Instead of lambda, I went with lam. But again, that is kind of inconsequential since these are separate models that won't be won't cause any deleterious effects. And you'll notice that instead of lam 1 through 5 and 6 through 10, I have lam 1 through 5 and lam 1 through 5. So just as in kind of M plus, if you're more familiar with M plus, you can throw equality constraints in parentheses following a by statement to specify fixing a factor loading to be equal to another variable that shares that same label. We do the exact same thing in lavaan, and that's indicated by the lam1 star or asterisk. Everything else is identical, all right? And you will notice here at the bottom that I have this extra piece and it's extra syntax. It's not really needed. But if you use a different method of estimation where you use a standardized factor, then you will actually need this syntax to free up your factor variance. But because we are using the marker method where that first item is automatically fixed to 1, which you will see here, this is an unnecessary piece of syntax, at least in this context, but might be needed depending on how you are estimating or testing your measurement invariance. All right. So no need to worry about that. I'll actually delete it, but that is why that is there. So let's run the CFA model and test whether or not there is metric invariance. And so what I will say is, whoops, and actually that's a great example. So I had mentioned earlier, if you don't include your objects with all of your results, you don't get anything, and that's exactly what happened here. And so you see all the blue text, so everything is working really, really well, but we don't have any results. So if we actually just run these fit statistics and these outcomes, there come our results for our metric model. So we'll look up here, and lavaan ended normally. We still have the same number of people. We have 33 degrees of freedom, which is the correct number, the correct increase in the degrees of freedom. And the p-value is non-significant. The test statistic, the chi-square value went up. It will always go up as you place more and more restrictions. We just don't want it to go up and it be significantly different than the previous model, which I will tell you, spoiler alert, is not significantly different. We also have CFI and TLI. Both of those are looking really, really strong. Both are 0.99. And again, relative to the previous model, there's no real change. Our RMSEA went down just a skosh from the previous model and is still looking really, really strong. So our RMSEA is looking good. Our SRMR actually went up a little bit, but again, SRMR in my experience tends to not be a fit statistic that does a lot of distinguishing. It generally behaves really quite well, but it can be a really nice fit statistic if you are kind of on the edge of something where you're kind of getting contradictory information. So SRMR in either case, in this example, is looking really, really good. We want this 0.05, 0.06 is a very general light rule on kind of where we want that value. All right. And so you will see in the metric model that our lambdas, our value labels are showing up, and they are the same across male and female. So this is a really nice way to check yourself to be sure there's not a syntax error. Um, lam1, lam1, lam2, lam2, lam3, lam3, lam4, lam4, lam5, lam5, and you get the point. Or you could check your actual factor loadings. Are these the same numbers? 1.245, 1.245. So nice way to double check yourself. Actually, I can make this a little bigger. Our covariances, again, these were there before. These have changed perhaps a little bit, but they're not all that important, at least at this stage. And again, we haven't done anything with the intercepts yet. That's actually going to be the next step. The variances, again, not really all that important, at least at this point, and then our R squared, which is how much variance is being accounted for in our observed variables by the latent factors. All right. And so here you will notice that I kind of told you that we have non-invariance, that by restricting the factor loadings to be equal across the male and female groups, then we don't have a significantly worse fitting model. And so we can say that the latent variables are measured in the same way. They are indicated by the same variables and to the same extent. So that's what we can conclude, but I haven't given you a statistical test from which to evaluate that. And that's actually what I'm going to do following scalar invariance. I'm going to show you how to calculate the chi-square difference test. All right. And, the reason I'm not doing that now and I'm saving that for the end is what I generally do. So I can keep myself in check is I just run configural metric scalar back to back to back. And then I just look at the difference tests all in one shot. So that's a way that I can keep myself honest and avoid those tempting modification indices, or if I have a bad fit on my configural model, then I might be tempted to make some changes that weren't necessarily hypothesized, and that can lead to all sorts of errors if that's done. And if you think about kind of like the statistical decisions that you make, if I make a decision really, really early on in the configural model, that's going to affect the results of the metric model, the scalar model, and then eventually the full structural model that we're going to use within structural equation modeling. So that's a way I kind of keep myself honest and hold myself accountable. And so that's the gospel according to Mike on that one. All right, so we're going to finally test scalar invariance. So as you'll notice, this is exactly the same as metric. And the only difference is that rather than tau 1 through 5 and 6 through 10, you probably know where this is going. It is now tau 1 through 5 on both. All right. And so that is constraining those intercepts to be 0. So what the item intercepts tell you, because it can be a little confusing, a little ambiguous. Think back to multiple regression where you have y hat equals beta naught or beta 0 plus beta 1 x1 plus beta 2 x2 plus e. And what is that beta 0 represent? How does that interpret it? Well, it's the value of your y when all predictors are 0. And so that is the exact same interpretation within the structural equation modeling world. So this will be your intercept will be your predicted value on that item when the latent variable is 0. That doesn't mean there's no quantity of that factor, but it means, again, because honestly we standardize our latent variables, especially those exogenous latent variables. By default, they're often standardized, and so they're going to be put on a z-scale, and so negative values are interpretable. All right. So again, if you see If you see a negative number, it does not mean that there are potentially any problems, especially when we compare those latent means. And so that is what the intercept represents, and that will be more and more important as we move into growth modeling or structural equation models where there is a mean structure, because most of the time we don't really care about the means. When we talk about in linear regression what the interpretation of beta zero is, but very rarely is beta zero actually of any type of substantive interest. We care more about those slopes and those estimated parameters. And we're just moving a conditional mean up and down that y-axis, and we don't really pay much attention to that. And that is very much true for the structural equation model as well. But that becomes more and more important again as we get into models with mean structures. All right, so the other thing that I should talk about, that we're going to estimate and code, is we are going to freely estimate this latent mean. All right, so what we're doing is by constraining those item intercepts to be equal, we are now actually able to compare levels of the latent variable of latent relationship mindfulness across gender. And if you go back to the very first analysis you learned in your undergrad stat or grad stat, it's probably going to be the t-test. And so you had two groups, and then you compared means on those two groups. And so generally you dummy coded them to be 0 and 1, and 0 was the reference group, and 1 was had a meaningful value of sorts. So it's treatment and control. We're doing that exact same thing here. We are saying men are 1 and women are the reference group. So their means are going to be constrained to be 0. And in the output, we are going to get a value associated with this parameter. And what it is and what it represents is a mean difference on the latent construct. All right, and it's going to give us a p-value. And if that p-value is significant, that means men are higher or lower on relationship mindfulness compared to women. Right? And so the final piece of new information is the lav test. So I had mentioned in the metric model, or prior to the metric model, or prior to the scalar model, that we're going to do likelihood ratio tests, and this is the syntax for those tests. So we just enter in this syntax, and then we have the fit objects for all three of our models. And then lavaan does this beautiful thing where it goes in and it conducts a likelihood ratio test for us. And lavaan does it via the chi-square statistic. You can also do likelihood ratio tests with the D statistic, which is your -2 log likelihood. That's another version of a likelihood ratio test. And so we are going to estimate scalar invariance. All right, so we'll start at the top as usual, just to be sure that we've coded everything correctly. All right, so we have 305 folks, so that's good. We didn't lose anybody. We have a non-significant chi-square statistic, which is, again, it's good. This p-value has gotten bigger and bigger and bigger, which means as we've placed more and more and more restrictions on the model, it is not harming the model. We are actually getting a more parsimonious model, which is actually better and to our advantage, particularly around statistical power. All right. Our CFI or TLI and TLI are still looking phenomenal. They're not really moving a whole lot because there's not really much higher you can get. Our RMSEA has gone down yet again. Our SRMR did not move this time, but everything is indicating that we have an awesome fitting model and that we have invariance across all 5 items at the loading level and at the item intercept level. And so again, it's nice to just double check. This should be exactly the same as before, so we can skip over that. But here is where we make a determination on whether or not we have actual invariance or not at the scalar level. So right here, these estimates. And so first you want to double check, is this one the same as this one? Do they have the exact same estimate? Because they should. And if they don't, there is a syntax error. And so it looks like everything looks correct. All of those match up perfectly. And then this last one down here, oops, I clearly got in the way. This RMM parameter, this is that mean difference variable that I had mentioned. This is comparing the latent means on male and female relationship mindfulness. And as we can see, it is not significant. So men tend to report 0.049 units higher on relationship mindfulness compared to women, but that difference is not statistically significant. So we can say for all intents and purposes, men and women have the same level of latent relationship mindfulness. All right. And then the last thing I will show is at the very bottom. So we need to get rid of that guy. All right. Here's our residual matrix. So now that we're kind of done with everything, this is where I'll begin to take more and more look in the residual matrix. I'm probably scanning it as I go, but again, much like the factor loadings and intercepts, I'm really only eyeballing things. But generally, if we have really good fit up top like we have, I'm not all that concerned with the residual matrix because things are probably going to work out. We might have a few things that we might have to think about, but for the most part, it's probably going to be all right. And so we can actually go through that right now. And so we have the residual matrix here. So this is going to be a matrix of z-scores. So all of these values in here are going to be z-scores. So if you remember from intro stat, your critical value for z-scores is 1.96. So that means anything above 1.96 is going to be significant. So what does that mean? If we have a negative 2.47, like we do right here, that means this relationship, the covariance or the correlation between relationship mindfulness item 2 and item 3 for men is underestimated and it is statistically significant. So it's underestimated in a statistically significant way. And this gives us, oh, that's our standard error. That is not the correct correlation. And I am not sure what happened with lavaan. I may have accidentally hit the broom. So let me just rerun everything real quick. All right. I hate that broom is right near that window expand button. All right, so we were down here in the residual covariances. So here we had zeroed in on item 2 and item 3, this guy right here. All right, so this is the standard error right here, and this is the covariance. And so this tells us that this is the level of underestimation. All right, and so it tends to be correlation of 0.07, negative 0.07 isn't necessarily something that is, hugely impactful. It's also not something that's, teeny tiny and is kind of irrelevant. So I would kind of think a little bit about whether or not, I want to do something with this information. But really what my determining factor is going to be to what extent is this value, this z-score right here, kind of outlying from every other z-score in the model. I have another z-score right here that's just above 2 and would technically be significant. Another one here that's just under 3. There's a couple that are, 1.97, so that would technically be significant. But I'm not seeing, there's a few that are significant, but I'm not seeing very many kind of hugely outlying z-scores. And so that to me gives me, again, quite a bit of confidence that our model is the correct model. We don't have a misspecification in there. And again, all of that is supplemented by we have really good global fit. And so we're not really finding a whole lot of local problems. That's not always the case. Sometimes you can have great global fit, but global fit can actually miss pretty substantial model misspecifications. So we need to always inspect this residual matrix, but here everything looks all vegan kosher. So finally, we'll scroll down to the or perhaps even scroll back up to wherever it is, the likelihood ratio test, right? Yeah. So this is the comparison of the models. So remember when I said that we will do the likelihood ratio test, and we'll talk about that in the scalar model. Well, this is the likelihood ratio test. And so we have our model, which is the configural model right here. We have our metric model right here. And then we have our scalar model right here. We have the degrees of freedom right there for each model. We have the chi-square value for each model. We have the total chi-square difference. And so this number right here, I'm creating a lot of boxes, is just this number right here subtracted from subtracted from this number. So 41.616 minus 40.04 is going to give you 1.57. All right. And it is going to be the exact same for these values, where if you add 41.616 with 9.9197, you are going to get 42.53. All right. And then, of course, there's probably going to be some rounding errors. So those are the statistics that we've already seen, and here is the actual test, the likelihood ratio test, and we want this to be non-significant. All right. So if this is significant, that tells us at least one of our parameters is non-invariant, and in our case, that would mean gender is moderating either the factor loading or the item intercept, and that would be an indicator of differential item functioning. Some of you who have done some factor analysis, particularly those of you in the IRT world, may have heard around differential item functioning, but that is what we have found. I prefer to think about it as parameter moderation, that gender moderates the one of the pathways resulting in a non-significant or resulting in a significant chi-square difference test. And then that would give us partial invariance. But in this model, we found complete invariance. We found all 5 factor loadings and all 5 intercepts to be completely the same statistically for men and women in this data set. So in sum, that is how you test scalar, metric, and configural invariance. For some of you who have been exposed to measurement invariance in prior SEM courses before, you may have heard of residual invariance. I don't find it all that helpful. I think it's exceptionally restrictive. It doesn't really happen a whole lot in the real world, and we don't really need it. We can, if we're examining just correlations in our structural equation model, we don't really care about means even, then metric invariance is more than sufficient. If we are moving to like a growth model where means begin to become more important at the latent level, then we will need scalar invariance. But there's not really any conditions that I've read about or know about where strict invariance, where we constrain those residuals to be equal, is a necessary property to have before moving on to more sophisticated analyses. So hopefully this has been helpful, and let me know if you have any questions.